I would spend some time to introduce our work. So thank you very much for your time. Yes. Okay, so now I just start. So the topic of our work, it's a procedure we designed so to solve the problems in graphs. Okay, so later I would spend some time to introduce the problem description and also spend some time to introduce our work. So especially we proposed a novel procedure, okay, to search something we want. So, and also in literature, we know that up to now we have many classical available results, of course, and we appreciate that. So today we only want to spend some time to share our work and the results with you. Thank you very much for your time. Okay, so later I would spend several minutes to introduce some terminologies and also the problems we focus on in this work. So we say we study a classical and a fundamental problem in graph theory, and we indeed admit. So this problem is fundamental and classical, and many researchers have very good results on this problem. So again and again, we just want to share our results with you. And then later after the talk, so we also would like to have a chance to discuss and hear the advice from you. Okay, so now this is a problem in graph theory, and which is a fundamental problem. So we introduce for 2 minutes, and we believe, so many of you may have already heard about the problem, the matching problem in graph theory, okay, the matching problem. So we know in graph theory, the subject we study is a graph, and denoted as a capital G, usually a graph. And the structure of a graph is somehow easy, but problems related with graph, somehow it's difficult. Okay, so the structure of a graph is easy because we only have 2 sets. So one set is the node sets, so the vertex sets. And another set is the edge sets. So the structure of a graph is just so easy and simple. And this is the easy case. Of course, so in some graphs, the weights may be imposed, right? The weights, that is on each edge, we may have the weights. But in our work, so we study general graph, but this general graph still be unweighted. So we study unweighted general graph. And then we just do not consider the weights on the edge. And again, so in a graph, the structure is just, it contains 2 sets. So one set is edge, one set is the node, the node, the edge. So for matching, this is, we introduce the mathematical form of this problem. And a hint is that nowadays, that is in the big data days, so we have many online problems. That is how to match the boys, the girls, and many other things. So, but here we basically describe the fundamental form of the matching problem. That is, we extract the mathematical parts. So then in general, a matching, so we say it is just a subset. So a subset of E, okay? A subset of E, that is a subset of the edges in a graph. And then we say subsets of edge, right? And again, so many of you may already know the definition of matching, but I just to complete our discussion, so I would spend 2 minutes to go through this. So a matching is a subset of edges. And then here it's an easy example to illustrate a matching in a graph. unweighted graph, but now we have already our work extended to general unweighted graph. So you can see that we have node here, the node here denoted as 1, 2, 3, 4, 5, 6, 7, 8, for example. So this is, you could impose the notation, like this is just vertex 1, and this is vertex 2, and this is vertex 3, and so on and so forth. So in this easy problem, in this illustration problem, we just have cardinality of vertex as 8, okay? So, and then you could see the edge. So of course we have the symbol here, that is the dashed one and also the solid one. So these are the edges in this example. Oh, so this is the edge, this is also the edge, this is also the edge in the graph, okay? So both the dashed line and also the solid lines are the edges in this easy example. So, but now you could see that some edges in this example are highlighted as the solid one, right? Yeah. So this just means illustration of illustration of in the graph, okay? Yeah. So that as you can see still, it is a subset of edge, and the property is that it is so null of 2. So null of 2. That is in the matching. Here, for example, we have 3 edges here, okay? And null of 2, null of the things in matching meet at a common node. So this is the definition of matching, and intuitively we can understand the meaning of matching as well, because we just match the vertex 2 with the vertex 3. We match these 2, right? And also we match 6 and 7 here. So the vertex 6, and the vertex 7, these 2 nodes are matched together. And then easily, so vertex 4, vertex 1, so these are matched together. So which means that intuitively, the concepts of the terminology, it's easily understand. So we can know the meaning behind the terminology. And mathematically, we just say matching in a graph, it's a subset of capital E, a set of the edge, okay? And we have some requirements. And in this work, we present here, that is we pay attention to some crucial and important ones, like we say maximum, and also the perfect one here. So, and also we have perfect matching. So this is what we want to identify and search in a given graph. And we say that, okay, so this is where we want to study. And later in this paper, in this work, indeed, we propose new procedure. So, and the nature it's depth first search algorithm, okay? So this is the nature we would introduce. So we would spend some time to introduce how we initialize our procedure. And also we use some good examples to illustrate that is our procedures indeed work. And again, so we admit this is a fundamental and classical problems in literature. And definitely there are many updated and very well-developed procedures to handle this. But still, we believe the contributions of our work. So first is that's very important. So we think the data structure. So the data structure in our procedure, it's really simple and good. So it's elegant, okay? And and simple. Yeah, so not very and also the complexity of space and time would be dramatically improved. So that is the complexity. So of course, all this information can be identified and found in our paper, but I want to highlight a little bit. So the data structure of our work, it's really inspiring, okay? So later I would spend some time to introduce and more, okay? And also we could use some examples to show. So then you would see, wow, so the structure of the procedure is really easy. So whether indeed we can achieve our goal, that is to find a perfect one or one in a general unweighted graph. But indeed we can, because we spent around half a year to implement the procedure in Python. And also we have tested on thousands examples. Okay, so, and then again, the data structure is simple. So we first highlight a little bit here. That is nature, we only have 2 linear. So nature, we only have 2 linear stacks. Or we could say arrays. Or we could say stacks or arrays to store the full information, yeah, in the searching process. Okay, so if we talk about the major thing we have and designed in our work, I think the data structure is good. And also the second thing we want to identify and highlight is that our procedure is designed with a very good stopping rule. So the stopping rule is clear. Yeah. So the stopping rule is clear. Okay, so the stopping rule is also clear. This is what we want to highlight a little bit. And yeah, we just spent several minutes to introduce the meaning, the basic, the intuitive meaning under the terminology, and also mathematically, what is the meaning of it? And also, what do we want to handle? What is the problem we handle in this work? And also, we just spent 2 minutes to highlight what is the major achievements. So the data structure, later we would introduce just with 2 linear stacks. And our stopping rule is clear. We say we stop, that it's, we either stop to identify something, or we conclude we cannot update the current one anymore, okay? So later we would introduce a little bit more, but this is what we really achieve in our work. So in the slides, we also spent some time and efforts to list some classical results in literature, because we really appreciate and know. So this is a fundamental problem, and we have plenty good results and great results available in the literature. Okay, so you could see that this is really a fundamental problem in combinatorial optimization, and we really admit it. So previously in literature, we have really great works that it's started the bipartite graph, so which is a special graph, right? A bipartite graph. And also in literature, we have works on general graphs. And this is also a great work, yeah, so we know. And then later in literature, some great scholars have improvements on the complexity of this problem, and so on and so forth. And around 3 years ago, we just have a chance to revisit the greater the great things available in the literature, and we have some discussion, and then happening that we just designed something, and we spent plenty of time to double check our solution and the procedure, and also double check and carefully implement the procedure. And we test the procedure on numerous examples. So now we just happy and want to share the results, okay? So in our work, we just proposed and designed a DFS procedure. So we say it is complementary to Blossom procedure in literature. And we really know the Blossom procedure is great and great. But when we do comparison, we just simply want to say the key features. That is in literature, in this famous work that is published in 1965. So BFS, that is, we say, breadth first search. So we just use 1 or 2 minutes to introduce what is the thing we have here. Because for BFS, that is start from something. A tree will be a tree would be so we just gradually generate a tree. So a tree would be generated. So which means that in a procedure, we always start from something. Later, I would introduce the terminology. And again, so I believe some of you are well known of it. So we start from something. That is, we start from, we say a node, or we call it the terminology. So free vertex. Free vertex, okay, and we say the node is free, but we want to highlight free with respect to current matching, okay? So that is always we start from something and then we update it. So how we can update the current one, the initial one, and to achieve the ultimate one we want to get. So this is a key part, right? So in the classical BFS procedure, so we say start from something, a searching tree would be generated. So a searching tree would be generated. So which means that this procedure is really great. And nowadays, many other procedures are designed based on it and to improve the data structure based on it. And this is really a great work. But still, in this BFS procedure, a searching tree would be generated. So which means that in many examples, especially nowadays, the number of nodes and the edge would be huge. So then a searching tree really occupied the space and complexity. Okay, and then still we want to emphasize in our work, the data structure from the very beginning to the end. We just have 2 linear array. Or we follow some papers, we call it stacks, okay? So, and we want to highlight the good part, that is linear always. So which means that in our procedure, the data structure is really simplified and we really can achieve what we want to search. So now we mention a little bit here. For the 2 linear arrays, that is, we know in a graph, we have capital V and capital E. So indeed here, so when we say we start from the very beginning, that is, we start the search, and always the 2 linear arrays, one array would be the array of the edge. And the other array or the other stack is about the nodes, the vertex. So this is a first introduction. Later we would see how start from something and how we always use two linear arrays to store the whole searching information, and how we update the information in the two linear arrays along the way, and then finally, anyway, it is updating, okay, and then we just stop with a stopping rule, okay. So so now we may have the question in our mind. So how to stop, and at what scenarios we would stop. So later we would gradually introduce. But again and again, we admit, so many great and well-developed results are there. And just 3 years ago, we have a chance to study and revisit these great available results in literature. And after some discussion, after half a year and a year, we just have a chance to identify something and implement something. And we believe this work is really interesting and good. And we want to share with you. And we have already summarized many results in our technical paper. Okay, so this is previously where we have highlighted a little bit. So now I would continue, okay, yeah. So I already spent many time here to emphasize the work and also the motivation. And for the complexity, we just highlight here, and this can be found in our technical paper as well. But what we want to highlight again and again, okay? So in our work, we only need two linear arrays, two linear stacks to store the information. So this is really we want to highlight. And there are plenty of terminologies in the literature, and we summarize some in the slides, but I think the time is limited. We highlight here, but after the meeting, we can discuss more as well. So, so a very important thing is that where we start from the search, we say we start from a node. So, and then we say always we have something available here, and we update it. So then the thing is that starting from available aim, the matching here, and also we want to update it, right? So the cardinality of aim. So we want to do something. We want to enlarge the number of edge in aim. And then there is well-known results in literature, and our DFS procedure designed based on it as well. So that is the condition here. This is a classical results in literature, and this is a if and only if condition. So the BFS procedure depends on it, and our DFS procedure depends on it as well, because indeed it is if and only if condition to guarantee whether the edge of aim is already enlarged to the sense, right? So this is a if and only if condition. And then how we update it, we say special path is important. So we know augmenting path is important. Augmenting path is important. So in our DFS work, indeed, we start from some nodes, like denoted as V0, so which is a free vertex with respect to the current, okay, denoted as aim or aim none. Those will be fine. So we start from this, and we want to search augmenting path as well. We cannot avoid this because this is a if and only if condition. But the key point is that we start from V0, how we can identify and design a DFS algorithm with just the two linear stacks and with a good stopping rule. And we say that, so starting from a free node, So whether augmenting paths, we can definitely tell exists or not, because if starting from V9, the augmenting path, okay, V9 is here, okay? So an augmenting path can be identified. Then we say the cardinality of the current aim can be enlarged by 1. And if we can definitely conclude, starting from V9, there exists no augmenting path, then we just stop. And the current aim, it's already the aim we want. Because again, the Bojun lemma, it's if and only if condition, we cannot avoid it. But the inspiring part is that in our searching of augmenting paths, we really only need 2 linear steps. Okay, so there are plenty other properties. We summarized here, and we have some of them included in the technical paper. But now I want to spend some time to introduce the setting of the searching procedure. And also we have some illustrative examples, okay? So we have a detailed and focused observation on the augmenting path, because we say augmenting path, we can't avoid it. It is an if and only if condition. But we have a many detailed and focused observation on it. So, and then another inspiring thing is that in our initialization of the search, we just give the edge the color. And then we have, so we color the edge. And if you have time to read our paper, you could see the coloring technique, the coloring skills. It's really special. And then this way of the coloring of edge could help us to identify more structure of the graph. Okay, so this is really interesting and important. And I would first show you some examples or fit the graphs. Okay, so that is so we give the edge the color because we use it to facilitate us. In a graph, we just have V and E and nothing special. But now we have the right. So we have the edge with the red blue. What do we want to do? So the thing we want to do is we want to identify and present the structure of the graph better. The structure of the graph better, because indeed we only have V and E, and this is and we want to identify M, which is a subset of E, and also the cardinality of M, it's enlarged, right? We maximize it. So this is the combinatorial problem. So nothing special with the color, because we do not color the edge. We say the color here, what do we want to do? That is, this is the initialization step of our procedure. And a very important thing is that we want to present the structure of a graph in a better way. And this is a part of the initialization. And another crucial thing we have is that for a single, so you see, in a graph, so we just color it with 2 parts, So that is the terminology here. But this is really interesting, okay? So I think because of the limited time, I just first introduce the key points. So here, for example, we have the path, right? We want to search. So the key parts we want to, the very important parts we want to identify is augmenting path. Okay, and then we say for each edge, we just have 2, we just separate it into 2 parts. So this is still one single and just 2 node here, but we just give it 2 colors. And then we have initialization of our DFS search, okay? So I think the time is limited. So maybe just another 5 minutes. Thank you very much. So we say we have for planting graphs, right? We have the edge and also the node. And when we initialize our search, very important, we give the edge the color. And the red, blue are important because I mentioned a little bit. So for each node, so you see in a graph, we have the node, right? And also the edge, you see. So starting from each edge, we only have half of it. Let it be colored as red. Okay, and then you could see that a very important feature is that for any node, you see, if you look at the thing here, you see, so just the one red, you see, for V3, just the one red, the other is blue. And for V4, just the one single red. For V10, just the one single red. And this red, it's this half red, it's for V9, and so on so forth. So if a node is incident to more than 2 edge or 3 edge, like V2, indeed, the other 2 half are blue, only one single is red. And then in our searching procedure, we just really update something. And then we update, and then you see that later, if the red parts for 3 and the red parts for 2 matches with each other, then this whole red parts, I see this is an edge in capital M, because capital M is indeed a subset of the edge, right? And this kind of edge for 2 nodes, you see, the half red for V2 and the half red for V3 meets each other, and then we say, oh, we achieved this edge in capital M, So just the 3 more minutes, and then you could see I highlight and show you the initialization. And we have included planting examples in details in our technical paper. So the initialization of our searching is that we just propose the coloring configuration to our graph. And the key points of the coloring configuration I have highlighted. That is for each node and also the edge incident to it. Okay, so we only have one edge and with the half red, one edge with half red. So this is the part of the initialization. That is, we have a node, you see, we have planting edges incident to it. And then only one single edge and also half of the edge is colored as red. You can see that in Python, we could easily do it, right? We randomly select edge incident to a node, and then we just do this color in this way, you see? So this is initialization. That is coloring configuration initialization. And also we propose 2 empty linear stacks. Empty. So one list or array or stack, you see. So it's for the nodes. And another empty, it's for the edge. But we have give this name like a trunk, like sprouts. But the key point is that for an empty trunk list, the trunk list, actually it's a list of nodes or a list of the vertices. So a list of the vertices, an array of the vertices. And this is starting from a free node. So starting from a free node. And this is the first starting from a free node. Second, it is alternating path. And then we continue the search. If the alternating path successfully stopped with an augmenting path, then we can augment and update the current capital M. And the cardinality would be enlarged by 1 and so on and so forth, right? So because for alternating paths, many of our node terminology alternating paths and augmenting paths. Okay, so we always start from a free node with respect to the current capital N and alternating. That is one edge in A, one edge not in A, and so on and so forth. And for augmenting paths, that is this alternating path, also with an end point. The end node is free with respect to current aim as well. So we always start from a free node with respect to current aim, and we search alternating paths. And the desired goal is that we stop at another free node with the current capital aim, and then we have ability to augment and enlarge the cardinality of the current capital aim. These are key points. And this initialization, it's kind of clear and easy because you could see how easily we can implement in Python. And then crucial things are the while loop and the if conditions. We carefully designed, okay? We carefully designed. I think today the time is limited. And indeed, we have plenty detailed observations on the structure of the problem and graphs, okay? So another key point and crucial problems we highlight here is that when we want to design a procedure to search capital M to enlarge the cardinality, that is cycles are really important. Because you can see that we started from V-non and we started the search, right? So one in aim, one not in aim, one in aim, because this is free with respect to aim, and then so on and so forth. So when we search an alternating path, there is a crucial problem. That is, we may encounter the cycles, and especially we care about even cycles. So in combinatorial sense, if we have a cycle, right? We have a cycle. The cycle is either odd or even, which means that the length of the cycle is either odd or even, no other chance. And then in, so we have a cycle and we have an edge into it. So we say that up to now, we already have the coloring, right? So we say that we just have a full red color edge or full blue color edge into the one. So we can prove and do careful analysis, and then we could say that only the first two combinations are possible, and the second two combinations are not possible at all. So we have detailed analysis. And we introduce here a little bit, just want to highlight. Indeed, we have spent plenty of time to carefully study, and do observations on the structures. And then another key point of the searching problem is cycles. And this is also the crucial problems solved and in the BFAs, that is in Blossom, the classical and great work in 1965. So when the cycles handled in this work, that is a Blossom, the concepts of Blossom, the technique of Blossom is introduced, right? That is, if we encounter even alternating cycle. So in this classical and great work, so this kind of cycle, it's shrunk. That is shrunk to a macro node. Okay, and then once this cycle is shift, so it's so we deal with it, right? So and we just shrink, or the cycle is shrunk into a larger node, and then this work has the chance and the possibility to go forth to searching the augmenting path. And also, when the searching stops and ends with another free node, then later the cycle would be unshrunk and so on and so forth. But if you have a study on this problem, you know that the structure of graphs in general is really difficult. because when we search the path and also we encounter the so the cycles may be chained together, and also maybe one cycle is contained in another one, because in the structure of a graph, so the topology or the structure, it's just complicated. All of the things are involved together. You just really difficult to identify a good condition. But this is really a great work and happening. We just have a chance to say that by using two linear stacks, we are able to save all the searching information. Okay, so maybe today the time is limited, and I just highlight some key points. Okay, so in computer, and also in computer, we implemented for half a year, and we have tested the procedure in numerous examples. And we also have some handwritten notes and to do careful observation and so on and so forth, and planting good examples. Like this classical example, I used 1 minute to mention. So it has 2 leaves, and for this example, perfect one not exists. And we use this example to double check and confirm whether when our procedure would stop. So actually, the stopping rule is also mentioned in the paper. So that is we have an edge called the sprout list. So this is a list of the edge, right? And also a trunk list. But actually, this is just save the information of the alternating path starting from a free node. And then it is a list of nodes and so on and so forth. So when we stop, that is, we just enumerate all the possibilities. And then the sprout list ends with no elements there. And still augmenting path not exists, okay? So I think really I need to stop here, and then I would show you some examples. So this is an example proposed by a scholar in India, okay? And this is an easy graph, but well designed. That is 2. So the cycles here are chained together, and then we just, previously there is a mistake. So we care about and also the other one is important, okay? Because that is when we into the cycle. So we have 2 ways, because you can see the alternating path red, blue, if it is in this way, that is red, blue, red, blue, red, red, blue, red, blue. Never mind, okay? So let me see. Even 1, 2, 3, 4, 7, 8. This is even. Okay. So this is not the case. 2, 3, 4, 7, 8. No. So let me see. So maybe we just use an example in the paper or a Peterson graph. So we just have plenty examples, okay, to illustrate that how the color, how initially we just apply the color to a graph and to help us identify the structure anyway. So like here, so you see just 2 minutes. So once we give the color to the graph, previously just the edge and the node, and for each node, you can see just half of it is red. So this half red is for this node, and this half red is for another node. And if 2 red parts, you see, half parts are meets each other, then this is an edge in A. And then you can see the green points here, just with a half here, right? And for the other one, this is blue. So this is free with the aim, so on and so forth. So we have the initialization. And then the crucial point, of course, it's how to identify augmenting paths starting from a free node. And then indeed, just a list of nodes and a list of edge plays the role, and all the possibilities, all the alternating possibilities can be achieved. Okay, so in the technical paper, we have introduced some example as well, and this is another classical example. I think today maybe we first stop here, and I just want to conclude and highlight the key points of our work. The achievement is that the data structure is easy and with pretty clear stopping rule. Okay, and then just because the data structure is simplified, the complexity of data structure and the complexity of time space can be improved. Okay, so and indeed we have spent more than 1 year to run on numerous examples in computer, and the implementation work goes on for half a year. And then another thing we want to highlight is that some theoretical properties are discussed as well. So we have other nodes, and we have introduced some theoretical results. That is the properties in matching theoretically in the paper as well. So this is to handle the general graph. And then like components, the other components, the even components, something would be further discussed. Okay, so but now I think maybe today I first stop here. Thank you very much. And then to save your time, and then it's a Q&A. So for the honored and the great procedures proposed in 1965, so I just list some here, but this is really great work. But today, I think because time is limited, we just skip this part. And this is really a great work in literature. Yeah. So probably today I first stop here. Yeah. So maybe some parts are introduced not so clearly. But first, it's that because of time limitation, and the second is that because really we have many observations and the previous detailed discussions, and this is and the graph theory kind of easy, but the properties and the structures are really complicated. So in this 30 minutes, I think I want to highlight some key points in our observation and the key achievements we have there. Okay, and we really appreciate your time. Then I would first stop here. So if you have any problem, please feel free to propose. And also after the meeting, the conference, you can send me emails. So send us emails, and then we would find a time to reply your questions. And again, the implementation in Python, we have spent plenty of times, over half a year to implement, and over 1 year to run on numerous and large scale examples, randomly generated examples. So again, this work now it's for general graph, for general unweighted graph. Okay, and we have the achievement here. So very good. So now I just stop here.